Wasabi, you guys. We have a weird, awkward looking limit integral, right? If you try to, let's see, what would a person would usually do? Someone might be usually doing letting u equal x to the power of n, and this would give us x n minus 1. Well, we don't have that, so we technically have to do a force u substitution, right? So we have 1 over n, and then this is going to give us 1 over n, u of 1 over n minus 1, du equal dx. So what this means is that we get left off, let's see, ooh, wait, but then we get 1 over n square. Huh. Interesting. Yeah, I don't know how that's gonna... Oh, well, we already have the n, but sine of u du, right? This is just gonna converge. This is gonna equal to 0. I guess that equals to 0, but would you trust it? Do you trust it? Do you trust that? Huh? Let's figure out another way to do it, maybe. Huh? Because that's a little sketchy. A little sketchy. We do know that we do need to kind of, let's say we do have to like kind of split this, right? Because x power of n is different between 0 to 1 and 1 to infinity. So, okay, so we split this from 0 to 1 plus from 1 to infinity, right? Okay, so from infinity, if we plug in infinity, this is going to become 0, but then we get 0 over infinity. I don't know how this is gonna, because we still get 0 over infinity. Infinity. Ooh, yeah. That might not work, right? So you're a little frustrated, and you just don't know what to do here at this point, right? Or maybe you could try something else. But I'm going to show you a integral property that we all kind of usually not, well, I wouldn't say ignore, because not all of us ignore this, but I myself completely forgotten about this integral property, and it's usually in calculus textbooks. They usually call it the comparison property. If a function is at a certain range, I completely forgot the inequality. There we go. For a certain interval, the bound interval for x between a and b, okay, then we have our integral inequality mb minus a, ab, f of x dx, then big M b minus a, and these two ends, they usually come from this. That's all this is. Okay, that's pretty much what this is. This integral is in between this. So what you're doing technically is you are taking this and you're integrating everything, integrate from a to b. That's all you're doing. You're integrating the inequality from a to b. So that's all that is. Why are we bringing this up? Because we're going to use this, and you'll see why. Okay, so using this integral comparison property, how are we going to do it? Well, we know that this is sine of, sine of x or sine of whatever the function inside of sine, it's always between -1. It is always in between -1 and 1. Okay, and then you just divide everything by n, and what do you get? You just integrate. You just straight up integrate. Take the limit integral. Or actually, I don't want to redundantly write the limit, so I'll just integrate. Just straight up integrate the entire inequality. And what this does, we take the limit now. When we take the limit across this L, okay, this is what? This is just going to be -pi/2 over n. Take the limit. This is going to equal to 0. Okay, take the limit here. Okay, when we take the limit across, right? This is pi over 2, but over n, take the limit to infinity, it's just also equal to 0. Oh, okay. Well, I guess it seems like this is equal to 0. So, in which it does. So this integral is equal to 0 by squeeze theorem. Okay? So what we did is we used comparison property. And then we use this to helpfully set up our squeeze theorem, and that squeeze theorem helps us compute the limit. Okay, so sometimes whenever you do come across awkward situations like this, you could consider using the comparison property and then take advantage of the comparison integral property to use to compute the limit by using squeeze theorem. Okay. Alright, I hope that's helpful. Thank you so much for watching, and I'll see you guys in the next video.